switch on the transmission. Okay, then, yeah, welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, in Mexico. Our guest today is Dr. Kerem Camsari from the University of California in Santa Barbara. And let me say some few words on his vitae. Dr. Camsari received his PhD in electrical and computer engineering from Purdue University in 2015, where he continued on as a postdoctoral researcher between 2015 and 2020, before joining the Department of Electrical and Computer Engineering in the University of California at Santa Barbara in 2020. His PhD work established a modular approach to connect a growing set of emerging materials and phenomena to circuits and systems. His later work established the concept of p-bits and p-circuits as a bridge between classical and quantum circuits to build domain-specific hardware accelerators in the beyond Moore's law area. He is a founding member of the Technical Committee on Quantum, Neuromorphic, and Unconventional Computing within the IEEE Nanotechnology Council, where he leads the Unconventional Computing section. He has received the IEEE Magnetic Society Early Career Award and an Office of Naval Research Young Investigator Award for his work on probabilistic computing. He is a senior member of IEEE. Kerem, thank you very much for joining us, at least virtually today, and we are looking forward to your talk.
Thank you very much, Thomas, for that nice introduction. And it's great to be here to talk to you all. And I guess I slightly changed this title. I called it in the abstract massively parallel p-computing with p-bits or MRAM technology. Doesn't matter much, as you'll see. These are quite linked to one another. And I'll try to give you a general flavor of these activities that we've been doing the past few years. This is my group at UCSB. I have, very bright, very nice young people who are, helping develop this further. So a lot of credit goes to them because, without their constant support, this would not have been possible at all. So let me, sketch a picture for you, just to talk about, computing today, where things are. Of course, you're all familiar with bits. This is basically powering our entire computing paradigms, right? Everything that we do it with bits nearly. And these are zeros and ones, and we have this abstraction. And we have amazing devices that represent these bits, okay? We have CPUs, GPUs, and you keep hearing about these XPUs, X being a different letter of the alphabet. CPU used to stand for, central processing unit. Now you have graphics processing units and you have tensor processing units. So what's going on, right? The interesting thing is there are billions, tens of billions of transistors. Okay, did I lose you? Oh, I got frozen for a little bit. I hope it's not.
I hear you perfectly.
Okay. I felt frozen for a second, but it's fine. So billions and billions of transistors, and that is basically incredibly impressive and growing bigger. But on some spectrum, you can argue that the qubits lie, right? Between there's bits and you keep hearing about qubits, and these are not zeros and ones, but these are these superpositions of 0 and 1. That's a technical word. We have to discuss what it means. And so it's not very easy to describe. For example, if you say that a qubit is 0 and 1 at the same time, that would not be quite correct, right? So the qubit is this funny object that requires a technical description to even talk about its basic properties. Nonetheless, we are seeing this enormous activity from major players, companies and governments are investing in this technology, and they're trying to build these quantum computers that will harness or use this amazing powers of qubits, right? So, but these look quite different, but there's a unifying theme, and that theme is this idea of domain specificity. So what does that mean? If you look at what's happening in bits, you're seeing these emergence of GPUs and TPUs. They are specialized machines to accelerate specific applications, mostly in machine learning and artificial intelligence. So they're not meant to replace your normal computer, but they are meant to do certain things much better. Now, quantum computers are a little bit like that. Quantum computers are not, even in their beautifully scaled, imaginary, ideal form, they would not be considered as serious replacements for everything, but they would replace basically certain things. For example, simulating quantum mechanics, or taking a condensed matter system and trying to understand its ground state, or something like that. Something that's very difficult to do would be, so there is this rise of domain-specific hardware in this beyond Moore era of electronics. Now, you see, where do p-bits lie in this space? We like to argue that p-bits lie in between. Okay, they lie in between bits and qubits. And this is not just a cartoon picture. We really think that, you know, in the road between bits to qubits, you have to pass through p-bits. And one easy, to a physics audience, I guess, one thing that's obvious is qubit is first and foremost probabilistic. So there is probability embedded in the quantum world. And of course, there's more. It's not just a classical probabilistic system. Qubits are really special. But the p-bit that I'm going to talk about today is really this idea that there's this object that's fluctuating between 0 and 1. In some sense, it's very classical, but it's not deterministic. So there's probability built into the update rules and to the dynamics of things. Now, p-bits, just like bits and qubits, are also about domain-specific hardware and architectures. They're not meant to replace everything, but they are meant to help with machine learning and AI, especially on probabilistic applications, and perhaps this emerging area of noisy intermediate scale quantum computing. Many of the applications that people envision there, we think you can do them, or at least get close to them, by doing stuff with p-bits. Now, this is the general. I like to give this big idea that's driving this field. That there are, of course, many others that are trying these domain-specific hardware and architectures for things that are very similar to probabilistic computing. I'm telling you our flavor of it. But there is this growing idea of this. Maybe I can describe it with the slogan, "Let physics do the computing." It's this beautiful idea that. That says that, okay, if you have a naturally deterministic problem, use bits, because they are physically, the bits are classical and deterministic objects. If you have a naturally quantum mechanical problem, then use quantum bits, because they will naturally solve the necessary many-body quantum problem for you. And if you have a naturally stochastic or probabilistic problem, use p-bits. Okay, so this is sort of this emerging idea in this field. And a computer-centric way of thinking about it is, anytime you solve a problem, there's a time it takes for you to solve the problem, and then there's the energy. And then, of course, some of it is dependent on the problem. This is like f of n and g of n is what comes from the mathematics of the problem. Like, okay, if I double the size of my problem, what happens to my time to solve it? This is a computer science way of thinking about it. But then there are, of course, prefactors that, okay, if I use a Pentium processor or if I use a Xeon processor, how long does it take for me to solve this problem? So energy and delay are really, functions of these two things, algorithm and problem-dependent functions, which is almost mathematical, which relates to asymptotic complexity. There's this complexity theory that tries to sort of classify these things. And then there's a device and architecture-dependent part, which is extremely important. That, okay, how can I improve my architecture? How can I get a better transistor to improve things and do them faster? And these are, in this new era, these are becoming really intertwined, that you're trying to find architectures and problems and algorithms to improve the energy and delay to solve our computational problems. Okay, and one could argue that Moore's law was all about reducing these prefactors. You were trying to make your devices more and more efficient. But in this beyond Moore's era, we have to understand the algorithm so that we can find an architecture that kind of does things more efficiently. Now, in quantum computing, as you know, one of the biggest drivers, or one of the most spectacular examples I know, is the Shor's algorithm, which changes the exponent, or that problem-dependent thing, in a remarkable way. Shor's algorithm for the specific problem of factoring takes this exponential n dependence on the problem size, which when you solve it with classical computers, it turns it into something like a logarithm. Now, I don't know a more drastic change, an exponential becoming a logarithm, right? Logarithm doesn't grow, exponential explodes. So that's why this is their pride and joy, this very important algorithm of integer factorization with quantum bits. Now, with probabilistic computers, we do not have such amazing algorithmic improvements yet, because one can say that many of these probabilistic bits, you can implement them using bits as well by the use of pseudo-random number generators and so on. More about that. This is just this general idea of let physics do the computing is becoming this very important theme in this beyond move era. So what are p-bits good for? I mean, before I'll describe to you how they look like, how to think about them, etc. But what are those naturally probabilistic applications? Well, one big area is this field of optimization. Okay, so this is this famous traveling salesperson problem. Okay, so let's say you're coming from Mexico City and trying to, revisiting Santa Barbara, and you say that, okay, I want to visit these 1,000 cities in the state of California, and I want to visit exactly once every city, and I want to come back to Santa Barbara. How do I minimize my distance? So this is this very famous, quintessential combinatorial problem where there are only finitely many routes for you, but it's very difficult to find the optimum ground state, basically, like what is the minimum path that will make me do this. So these have very good probabilistic algorithms. In fact, one of the most successful probabilistic algorithm here is the simulated annealing algorithm, which involves probabilities. Okay, so whenever you have a successful probabilistic algorithm, p-bits become a very natural choice to solve those problems. And in fact, simulated annealing is probably the most successful algorithm in some of these problems where there is nothing else to do. You use these probabilistic algorithms to solve such problems. So in that case, a p-bit, which is a sort of a hardware realization of these probabilistic building blocks, is often very good. Now, there is this other area, if you're familiar with the statistical lingo, they use these words optimization and sampling. If you're not familiar with that, don't worry. But there is this other area where p-bits could make a big difference, and that is this artificial neural networks that are statistical inspired. These statistical inspired probabilistic machine learning models, we can express them very nicely, very naturally with p-bits. And one striking application, this shook the sort of physics community a few years ago, is you may be familiar with quantum Monte Carlo methods, where you sort of try to solve the quantum many-body problem using probabilistic models. But this shocking idea from Carleo a few years ago was that if you throw machine learning at the problem, which is sort of the fashionable thing to do these days, because ultimately your many-body quantum problem represents a probability distribution. And maybe I can find a way to learn that distribution. Maybe I don't have to simulate this complicated physics. Maybe I can throw a good machine learning model and it can be successful. And they showed that it's actually very successful. But I'd like to remind you that all of this is done in software. And what we are trying to argue here is maybe you can design a computer that will do these things by orders of magnitude more efficiently and faster for you. And I'll show you some results that's going to point to the relevance and evidence of some of those claims. Now, are these the only ones? No, there are many applications. I mean, here's a chart for you that you can do, true random number generation, energy-based models, Monte Carlo methods, optimization, quantum chemistry, quantum machine learning. These are things that in one way or the other, we are really interested in. And with, so p-bits really, in my opinion, are really fundamental objects that really goes to the heart of many things that we care about in science and engineering. And that's why I think that those two are big examples, but there are many more that one can imagine with p-bits. Okay, so that's enough of a general introduction. Let's get to some concrete pictures and look at what this object is. Now, this is a p-bit can also be considered as this. If you use machine learning terminology, it's this binary stochastic neuron idea. Now, if you don't know what those mean, we're trading one word that you didn't know with some others that you didn't know. So don't worry about it if you don't know it. But if you know what that is, that's immediately clear to you. But I'm going to explain what it is. It's actually not very difficult. It's a binary state. The output of a p-bit is always a 0 or 1, like a Bernoulli variable or however you like to think. Okay, that's simple. The update rule is stochastic. So there's always probability involved when you make your output decision, whether you are 1 or 0. That's a big thing. That's usually a very useful thing. And a neuron is like, we're going to build something that resembles neural networks with these, or you're going to build these probabilistic graph models. So that's where the neuron thing comes from. You know, there is no connotation to biology here, at least not in any obvious way. Now, the input is going to be an analog number, which changes from -infinity to +infinity. And then the output will be, as I said, this digital binary thing or bipolar thing. It's either 0 or 1, or it's either -1 or +1. So how does this look? Now, if you, as a function of time, if you give 0 input to this object, it just fluctuates randomly. Okay, so it's +1 in 1 second, -1 in the other, and it goes on and on. And if you sit down and take an average, you should see a 50-50 fluctuations when the input is 0. Okay, that's the p-bit. And this I sub I, that input, sort of allows you to tune this probability. So if I put a +1 in the input, I get a little bit of more ones, still randomly. And if I put a little -1, then I get a little bit of more -1s. And also still randomly, right? That part is very important, that these are not periodic, but these are really quite random. And if you swept the input, the blue trace, from -4 to +4 in the background, you would see that you can pin this p-bit and essentially make it a bit if you really want it to be deterministic. But in the middle, when there's like a lot of, there's the input is close to 0, there's a lot of fluctuations. And that's the main idea. And if you sat there for a long time at each of these points, then you would see this shape that looks like a sigmoid or a hyperbolic tangent. That represents the average of the p-bit. Now, sometimes I confuse people with this average behavior. You have to understand the p-bit is not going to measure the average. It's always +1 or -1. So we're operating with +1s, -1s. The average just exists if you sit and wait for a long time. Okay, so that's actually a strength of the model. It can go beyond mean field stuff and really do complex time-dependent dynamics in high dimensions. Okay, that's very technical. If you didn't follow that last bit, that's totally fine. Okay, so I froze a little bit again. Okay, so there are a lot of implementations of p-bits with, I don't know if you can hear me. Okay, you can hear me.
Yes.
Okay, thanks. I probably on my end, I'm freezing a little bit every once in a while. So there are a lot of implementations with p-bits. You can have something like nano devices. You can have digital CMOS. You can have mixed signal CMOS. So this is an abstraction, and there's a lot of implementations with different hardware substrates. Okay, that's another big point that we should discuss. Now, let me show you the simplest P circuit, my favorite, basically. Let's say that you have 2 p-bits. These are basically 2 p-bits. They have an analog input and a digital output, okay? And they're connected by these conductances, these G0s that we connect them together. We connect the output of one to the input of the other, and output of the second one back to the input of the first one. So it's a very simple, 2 p-bit circuit. So what will this do? Well, if you don't have any connection in the beginning, let's say that the G0 is 0. Basically, we're not connecting, we're basically disconnecting them. And then we're kind of expressing the state of the p-bit to this 4-dimensional space, right? You can express state of both as 0, 0, 0, 1, 1, 0, and 1, 1. If they're not connecting as a function of time, you have 2 random objects that are kind of fluctuating. So what's the big deal, right? I mean, nothing. It's just this is uniform randomness in this 4-dimensional space, and you're like 0, 0 with equal probability, 0, 1, 1, 0, and 1, 1. Not very interesting. But if you put correlation, if you just introduce this G0 a little bit more, now they're talking to each other. Now you see in this 4-dimensional space, what the p-bits are doing is they are a little bit more likely to be 1, 1 or 0, 0. Why? Well, because if one of them is 1, it tells the other one to be 1. It says that, look, I'm 1. I'm putting you a positive I now. You should also be 1. Or if I'm 0, I'm telling my friend to be also 0. And this is sort of you're sort of increasing the probability of observing 0, 0 and 0, 1, 1. And that's kind of, that's what we are seeing here, that they get correlated. And you can do this with an inverter. You can say that, okay, if the p bit 1 is +1, invert that output and give it to p bit 2. And if the second p bit is +1, invert that and give it to p bit 1. Then what do you see? Then you see the opposite, that now it's more likely to be 1, 0 and 0, 1 than 0, 0 and 1, 1. Now, if you're a physicist, you can see that, okay, what have I done? I've engineered a ferromagnetic interaction and an antiferromagnetic interaction, right? But the thing is, the beautiful thing is now we can engineer this. Now we can take a complicated system and engineer and put these correlations into the circuit, okay? So this is really all that we're gonna be doing. Like all the examples I've shown you before, in some way or other, they rely on engineering these correlations, okay? So that's why it's my favorite circuit, because this shows you that even at 2 p bit level, we can start seeing interesting things, that as long as you allow this interactions between these probabilistic objects. Now, as I shown you that, okay, so how can this be more interesting? Well, I showed 2 p bits expressing 4 states. If I had 4 p bits, they would have expressed 16 states because it's 2 to the 4. And if I had 6, I would have been 64. And you see how it's going exponentially. So these number of states that you're engineering, you're going to be living in this enormous space. If you have 100 p bits, you are in an enormous computational space that these things are exploring. So this is actually making things rich and in fact difficult, right? You can understand the behavior from principles of statistical mechanics. And this is the really fun part, that you can use, for example, the way that I've described these to you is that you can prove that these p bits, if you run them for a long time, they will sample from the corresponding Boltzmann distribution, right? So there will be an energy associated with each state, and each of those states will appear with probability proportional to this exponential minus e, which is a very fundamental concept in statistical mechanics. Okay, and this is a field that you may hear, and that's sometimes called Ising machines or Ising computing, because the idea is often people will write down an energy that looks like the Ising model. This is one possible energy model that I'm writing there, which is like Jij MIMJ minus HIMI. This is the sort of well-known Ising model. But remember, these Jij's, in my definition, it doesn't have to be +1 or -1. Ising in the beginning was all interested in these ferromagnetic models. In this system, Jij could be anything. So you're thinking of some objects that are much more complicated. But these Ising computers are all about building hardware that will accelerate or that will implement such objects like p-bits, not necessarily p-bits, but objects like p-bits, and sort of sample from this Boltzmann distribution. Now, as you may know that quantum computing, that field often credits Feynman for starting that field, because there's a 1982 talk by Feynman, which you should check out if you haven't seen it. That says basically, okay, if you want to simulate a quantum mechanical nature, use a quantum mechanical computer, right? That's his basic idea there. Now, what's less well known is, before Feynman gets to quantum computers, there's a little passage on probabilistic computers. I mean, Feynman being Feynman kind of sees these things from the past, right? So this is a direct quote from the paper, okay? You can go check it out. The other way to simulate a probabilistic nature is by a computer C, which itself is probabilistic, in which the output is not a unique function of the input. And he's basically trying to, suggest that if you have a probabilistic problem, why don't you build your p-bits out of probabilistic objects? Why don't you build your bits or computer components out of these probabilistic objects? And to me, this goes back to the let physics do the computing thought. And it really is, in that sense, no different from trying to build these systems that are conforming to the underlying physics or the mathematics of the problem. Okay, so this is sort of the basic idea. I hope that gives you a small flavor of how these things work, how they can interact, and by engineering the connections between these p-bits, how we can build much more complicated things. Okay, so now let's talk about something more big and serious. So this is the p-bit. This is our building block. So how do we make a computer? How can we call something a computer? This is obviously not a computer. This is just a bit. Well, you can have, so this is a generic architecture, which is not very difficult. It's actually a generalization of that 2-bit circuit that I've shown you. You have n p-bits that you start with, so p-bit 1, p-bit 2, p-bit n. They each have inputs I and m. So I1, M1, I2, M2, In, Mn. And what you do is, so you take n of them. And remember, now these live in a 2 to the n dimensional space. But now what you do is you take their outputs. They're all digital. And then you pass it through this weight matrix or multiply, accumulate, or communication. This has different names. Sometimes people call it the synapse. Doesn't matter. All that we are doing is we're taking the outputs and we're creating inputs that will be fed back to the p-bits. What's that input? Well, it's a weighted sum. The analogy I like to give is you have 5 friends that you trust a lot. So you look at their state. They're all in agreement on some matter that you should be doing. They're all +1. And you trust each friend with varying degrees of confidence. You say that, okay, I trust my wife very much. I trust my father, my close friend, my mentor. And then you add it all up. And then you have a bias, which is your own opinion that, okay, in this case, I should really do this or I should really do that. So you add it all up, you get a single number. And then you weight it. This is the temperature of the situation. You'll see that this I0 is in condensed matter. You may know it as beta, which is your inverse temperature, right? So if maybe you are in an environment where you want to be more random, so you kind of choose a small I0 then, and that becomes your input. And that goes back to the p-bit, and p-bit makes a decision. That's it. Okay, this is the entire paradigm, that you have these objects that are talking to each other through a connection like this, through an interconnection like this, and they make probabilistic decisions. Now, what gets us really excited is, if you're coming from the computer engineering and computer architecture background, we like to imagine this as a clockless system. In your computer chip, there's usually synchronizing clocks, but here it's more physics inspired. You're letting them do their own thing, and things evolve as they evolve in nature. There is no traffic light. There is no synchronization. This is very important that I'll come back to. Now, there is this technical term, massive parallelism. Massive parallelism means in this context that the performance of the system, as I'll show you later, grows linearly with the number of p-bits. And I'm going to give you a metaphor to understand that in a second. And what we are also interested in, my group, we are interested in nano devices, especially spin-based devices. We think that there's tremendous opportunity for especially magnetic devices because they can build these p-bits really, really compactly, as I'll describe to you in a second. Now, this was the metaphor that I wanted to give you. This is the dream computer we want to build. Imagine on the left, you have a molecule, you have a box of molecules or asynchronously interacting objects. They could be people, they could be, this is a physics audience, let's stick to, basically gas, it's a free gas model, right? So they're weakly interacting. And what are the salient features of such a model? Well, first of all, it's massively parallel, meaning if you're counting the number of collisions on the left side of the box is entirely parallel to what's happening elsewhere. This is a parallel system. Nobody is waiting for anybody. Secondly, the interactions are local. You do not get to move a molecule here and expect it to instantaneously move something else down there. So it's a sparse model. It's a local model. And it is asynchronous. Nobody's waiting for anybody, right? So these are the sort of features of a physics-inspired system. And this is literally what we are trying to build with p-bits, that asynchronously interacting local models. There's a graph in the background. You can affect this p-bit through its neighbors. but then it's asynchronous, it's massively parallel. This is why the performance increases with increasing number of p-bits. You are having more samples and more computation as they're operating in parallel. Okay, so this is the sort of general picture that takes us from that 2 p-bit example to thousands. So where are we? I mean, let me tell you some facts, like what are the status of state-of-the-art P computers? Well, this is a 8-bit P computer, rather small and modest. It's not too big, that we've built with Nano Devices. I'll explain to you how this works in a second. But the key thing here was to show the noise on a nano device, like a stochastic magnetic tunnel junction. I'll explain what that is in a second, can be leveraged to build p-bits. Okay, so this was in 2019, and we've shown that, okay, we can solve difficult optimization problems like factoring integers and whatever with a computer like this. Now, as I mentioned to you, p-bit is not like a quantum computer, so it's you can build it or emulate it with classical bits as well. And what's better than using the best classical hardware today? So we recently built this in field programmable gate arrays. These are these. If you're not familiar with these are basically high performing chips that you can go and program, and you can use like pseudo random number generators inside them and really build an architecture that kind of looks like this p-bit and the synapse that I showed you in the previous slide. And we've scaled this up to 5,000 bits, and we've applied it to the integer factoring problem, and we compared it with other hardware in the field. Okay, so for example, D-Wave is a quantum computing company. They try to factor integers. We've really taken it to a whole new level because our own record was around 10 bits. D-Wave can do 18 bits, maybe, in specific instances. We were comfortably going up to 32 bits. And this is an exponential scale. You can see what happens to the number as you increase the bits. Okay, now let me mention, I'll come back to this later. We're not trying to say that this is an efficient way of factoring, because we still see an exponential difficulty. But this is just a very hard optimization problem. That's a great way of benchmarking our hardware to see whether we have built a good optimizer or not. We hope to use these optimizers for practically useful problems. But in this case, it's just a very hard test. Okay, and I'll show you that this is, even at the FPGA level, this is very competitive compared to GPUs and TPUs of today. Now, is that what we want to do? No, we want to take it to million bits, million-bit p-bit computers where they're really efficient, they're really scaled, they solve really hard optimization or learning or sampling problems. Maybe novel nano devices or maybe magnetic devices can take us there. So this is, this intersection of scaling this up is where I'm, basically very heavily invested in. And we're not the only ones. There are other people who are trying to build essentially probabilistic computers using maybe CMOS or other types of photonic devices and so on and so forth. So if you're not familiar with magnetic tunnel junctions, they're very simple devices. So magnetic tunnel junction, this is so the p-bit behavior is, this is what we want to build. So how do you build it with magnetic tunnel junctions? Just a little bit of more detail and flavor to you. This is a simple toyish, Mickey Mouse toy model of ferromagnetism. Well, the real ones aren't that much more complicated, is what I'm told. But here's a magnet model, which is, which separates these two states. Okay, and what you try to do in magnetism is to separate those two states by, let's say, 40 kT or so that there's an exponential barrier for that magnetism state to stay in some state like red or blue. And how people understand this is something like, okay, there's a prefactor that's picoseconds to nanoseconds, and I'm going to multiply that with something like exponential 40 or 60. And if you do that math, a picosecond times an exponential 60, I think that gives you some number of years. Okay, so that's why your fridge magnet stays there for 10, 15 years without falling off, because it doesn't lose its magnetic state. Now, the curious thing with exponentials is, if you reduce that energy barrier by, let's say, a factor of 40 or a factor of 10, then that formula predicts that you should be fluctuating all over the place. You should be going left and right in picoseconds to nanoseconds. Now, if you're an expert in magnetism, this picture is probably bothering you, because By the time you reduce the energy barrier to a KT or so, you cannot talk about the red state and blue state actually, because everything is available now to you. And it's not just that. So this is an approximate picture, and we understand, but this behavior holds even if you do the theory correctly. Okay, this is just a toy model. I'm just trying to tell you that this, if you reduce the energy barrier, this can fluctuate a whole lot. Now, that's of course very interesting physically, but in electronics, we need to read out states. So how do you read out magnetism? Well, the most successful device to read out magnetism, arguably, is this magnetic tunnel junction device. Now, you may be familiar with this. If you're not, don't worry. It's just a two-terminal resistor made out of two ferromagnets. And these arrows basically represent the state of those ferromagnets. Okay, it's pointing up or it's pointing down. And you separate them by an oxide. That's why this is a tunneling device. It's a very finicky, very interesting device. You have to optimize it. It's very difficult to fabricate it, but it's been tremendously successful in building, in scaling up. Magnetic industry have scaled this up to billion-bit densities. Okay, it's a very successful device. How does it work? Well, if the magnets are parallel, you get a low resistance. And if the magnets are anti-parallel, you get a high resistance. Then you can understand this by a simple circuit model. You can say that the electrons have a hard time going out if they are first polarized in some down direction. That's why you have a high resistance. But if you make them parallel, the electrons have an easier time going out. It's, you can construct analogies with the polarization of light. It's not a very, intuitively understanding this is not very difficult. Now, the world record, unfortunately, magnetics industry is really funny because they talk about these on-off ratios in terms of percents. They will say that our on-off ratio is 200% or 300%. What they really mean is RAP over RP is 2 or 3. So this is by transistor standards. To electrical engineers, this is really funny because the transistor on-off ratio is around 100,000 or a million. Maybe these days 100,000, but an object that can change its resistance by a factor of 2 or 3, that's not a very good switch. But still, the fact that MTJ has memory is very special. You can still detect a change of 2 or 3 in the resistance. And so this is how you read magnetism with MTJs. Now, what if I take one of those? Usually what people do is they fix one of those layers and it can't change. They only flip the other one, what's called the free layer. And that's how they can kind of go from parallel to anti-parallel. But what if I take and made one of those free layers, a magnet like this, a noisy magnet? What happens then? Then you see this very interesting behavior, and we see this in the lab with, MTJs that we get from our collaborators at Tohoku. It's the curious thing, it's a very funny thing that you have a resistance as a function of time that's fluctuating from 10K to 20K. And that's really, really strange, okay? Because you're not doing anything. It's just jumping up and down in the presence of thermal noise. There's some deep insight and physics in there as well, that it's a noise amplifier. You have only KT much noise in the system. You can turn that into hundreds of millivolts of fluctuations because it's really a collective phenomenon. Okay, so there's some very interesting physics here. Now, another, I want to tell you a quick story here that we predicted this a few years ago. Even 6 years ago, we were saying that these fluctuations can be very fast. And then we did it much carefully in 2019. And at the time, I remember there was skepticism in the magnetism community that people would say, oh, random walk is a diffusive process. It will never be that fast. You'll never be fluctuating at nanoseconds. This is all wrong. You guys are, this is just theory. But then last year, an experiment from IBM, not connected to us or our theory at all, they've shown that these SMTJs can fluctuate every nanosecond. This is an experimental fact now. 1 month later, another experiment from Tohoku. These are now our collaborators, but we are not involved with the experiment. They too showed an experiment with nanosecond fluctuating MTJ. So it's a very active field. The interesting thing is, I often wondered how in a field that is 250 years old, you can make these simple experiments and kind of, the thing is this, that people always knew that, the theory was always doable, but nobody cared about the low barrier limit because it's such a useless, irrelevant device. Magnetism without memory is so uninteresting. People you can see in these classic paper statements like, I can derive the low barrier limit, but I'm not going to bother because it's clearly irrelevant. So that's how we could write the theory in a very old field, because nobody bothered to explain these things. Okay, so this is, but for p-bits and like these new types of computation, these stochastic objects are very, very interesting. We're working more on these. There's more theory, more predictions. We're hoping that these will be these will be experimental facts soon. Now we're thinking, okay, maybe you can make both layers of the MTJ free, because without memory, you don't need to care about there is a fixed layer or not. Just make it simple. Just make everything random. Okay, so let's see if this theory holds up. We're still waiting to see if that's going to happen or not. I'm just showing you all this just to see that this is an active field where there are multiple players and kind of interesting developments happening. Now, let me quickly show you. That's all very good, but people always ask me, yeah, but that's a resistance. But your p-bit looks like a very electronic thing. So yes, more work is necessary. So what's that more work? Well, this is just a general slide where the STT MRAM technology. This is a transistor. This is a 1T, 1 MTJ transistor design that these companies are using. And as I told you, this is a very incredible field that they've already put 1 billion with a B, 1 gigabit MRAM and MTJs in these room temperature chips. So this technology has gone to an enormously advanced, but this is all for memory. So how do you make that a p-bit? Well, it's not very difficult. Well, first one, you can guess it quickly. You can see that you'll make one of them unstable, these layers, or maybe make 2 of them unstable. But this MTJ is now that object that I mentioned to you whose resistance is fluctuating. And you keep the transistor that was there, and you add 2 more transistors to amplify these fluctuations. And by some detailed modeling and theory, you can show that behavior as a function of the transistor input voltage and the output is going to look approximately like this p-bit behavior. If your MTJ is more performing better, that's going to look even more like this. You can right now be bothered with the fact that, for example, it doesn't go rail to rail here. So it's not quite a p-bit in the mathematical sense, but it still works and so on. And we can get into details about how this thing works or what are the approximations and so on. But now you see we have an electronic object that has an electrical input, electrical output, and it does this probabilistic bit computation that we wanted. So with Tohoku University, this is what we did. We kind of put this together on a PCB. This is what you're seeing, this tunable stochasticity. We have an input voltage at the transistor, and we were seeing that, okay, we can change the probability at the output. These were rather slow MTJs for the first experiment, not nanosecond, but these were milliseconds, and we were able to see this tunability, okay? And this is our chip. This is a PCB. This is 2 centimeters. There are 8 of them, but the architecture is exactly the same. They talk to each other through a microcontroller. This can be some integrated circuit. It can be some memristor. There are a lot of possibilities that one can imagine here, but that's the generic idea that you need to make them talk to each other. These are probabilistic agents. They need to talk to each other. And as they talk to each other, they can solve problems. Like in this case, they're on average factoring the numbers 945 into 63 and 15. So you run the circuit for a while and it kind of shows this peak emerges after 10, 20 seconds. Okay, so this was the idea. Now, let me not go to extreme detail on this, but let me just tell you that how do you solve problems? Is there a systematic way of solving problems with p-bits, especially optimization problems? And the answer is yes. You may be familiar with VLSI and digital design. What do we do there? We build copy gates, NOT gates, AND gates, OR gates, and then we combine them to make very big circuits like multipliers or filters or some logic unit, a GPU, for example. But it's all built out of the same building blocks. Is there a similar paradigm for this Boltzmann type computing? Yes. So for example, if you're trying to do a copy gate, that if you want to have p-bit 1 to copy, p-bit 2 to copy to the state of p-bit 1. So this lives in a 4-dimensional space. So you want the states 0, 0 to be emphasized and 1, 1 to be emphasized. This is a little like the example I've shown you earlier. And you do not want the 0, 1 states and 1, 0 states to be emphasized. So there's a systematic way of coming up with these interconnections. And you can do a copy gate, an AND gate, and even you can do composite gates. Okay, so there's a lot of information in this slide. It's kind of a cheat sheet, but it's just showing you that you can come up with systematically. The main thing that I'm trying to tell you here is you can systematically combine these things and make sure that the low energy states or high probability states are those that correspond to the logic that you're trying to implement. So for example, for the AND gate, you have 4 peaks. Why? Because this is an AND gate that does M1, M2 is equal to M3. Well, you see 0, 0, 0 pop up. 0, 1, 0, 1, 0, 0, 1, 1, 1. You see, so this is the idea. Now, how you get from the truth table to these matrices is not obvious, but it can be done and you can combine them. But you see, this gives you an enormous flexibility now, because now I can combine any circuit that I like and run it in reverse. Examples. For example, suppose you're trying to do a factorization. How are you going to do a integer factorizing? Well, because I can run these things in reverse, because this is now a generalization of an AND gate, generalization of a NOT gate, I can run this, I can use this p-bit-based multiplier as a multiplier. I give 2 inputs A and B, and I get the product at the output. Or I can clamp the product to something, and I can ask the circuit, what gives 6 at the output multiplier? What 2 products multiply to 6 or 9? Can you tell me? Can you find the consistent inputs that will get me 9 or 6 or whatever? So this is the power of this new way of thinking, okay, that you can run things in reverse. Because it knows the distribution, you can say that I want to see 9 at the output. So the circuit naturally wants to go to 3 and 3. Or if you're factoring 15, it tries to go to 3 and 5. Okay, so it's this very interesting. With normal VLSI design and CMOS circuits, you obviously cannot do it. The circuits are very forward, one directional. Our circuits are bidirectional. Okay, so that's this very interesting thing. Now, what is this complicated circuit? It's nothing but the schoolbook multiplication that you all know very well. How do you multiply 2 things? Well, you multiply them first digit by digit. Then you kind of add, you slide them and add them. That's exactly what this circuit is doing. These FAs are full adders, these are AND gates, and this is the product. But we can run this in reverse, as I said, and this, can kind of scales to enormous densities. Like you can, so this, what you're looking at is this simulated annealing plot where we have energy and we're kind of increasing beta. We're kind of reducing the algorithmic temperature slowly. And the circuit reduces its energy, reduces, and it goes and it finds a ground state. This is normalized to the ground state. That is 0 in this case. So it's really going to 0. And that ground state, because of the way we designed this circuit, corresponds to the unique factors of that semi-prime. That's a very large number. I'm not going to try to read it, but it has a semi-prime. It's the product of these 2 things. So now we can see that, okay, as a function of this inverse temperature, we see that the system is fluctuating in the beginning, all sorts of noise, but then it goes and it settles to the correct answer. This is nothing but a hardware realization, an extremely low-level hardware realization of the simulated annealing algorithm with p-bits. Just to kind of calibrate you, this is a pretty impressive number. It's a pretty impressive number, but it's a pretty stupid number. It's a pretty stupid number because if you go to Mathematica or MATLAB right now, as I'm speaking, you can give a 100-digit integer and it'll factorize it just like that. But it's not using a probabilistic algorithm. It's doing something else. Okay, so as an algorithm, this is not really good. But if you're thinking like a physicist, there's 2,000 p-bits in this system. The computational state is 2 to the 2,000. And you are finding 1 ground state out of that 2 to the 2,000 space spin glass. So it's as a spin glass problem, it's actually very interesting. And compared to other probabilistic solvers, it's much, much better. Okay, so this is like, you can check D-Wave or others. like it's 32 bits. I don't think people have even gone beyond 10, 15 bits, to be perfectly honest with you, despite these specific instances here. So it's very exciting. So what this tells us is maybe we can take these p bits, redesign everything from the ground up in this new way of thinking, and maybe we'll have useful optimizers. But as I said, factorization, please don't get me wrong. Factorization is a very hard benchmark problem. We're not competitive when it comes to factorization as it is. Okay, this needs to be much, much better. And here's the proof for that. If I plot the number of bits factored in the x-axis, time to solution in the y-axis, I see a very nice, very clear exponential. Okay, because it's a log plot. It shows that as I'm increasing the number of bits from 14 to 30, I'm going from 1 second to 10 to the 5 second. You're not going to factor a 2000-bit RSA number or a cryptographically relevant number with this way of doing it. You need to change that exponent quite a bit, okay? And maybe that can happen, maybe it can't. Maybe you can use this as a subroutine to some of those powerful factorization algorithms. We don't know. We just like to mention right now that it shows exponential scaling, and computer scientists call this type of problem that is easy to check but hard to solve, this non-deterministic polynomial time algorithm. We can get into that, but that's just the basic idea that if you give me the answer, it's very easy to check, but it's very hard to find that answer, okay? So let me, I'm coming towards the end here. How do you, another angle to consider here, how do you benchmark? How do I know that whatever I'm telling you that is relevant, that I can't do this in a classical computer? And the key metric we've identified is this idea of flips per second. So what is that? That is this idea that as you're talking to your friends, you're making a probabilistic decision, a flip, based on their input. You see, this is actually very important. It's a Bayesian, it's a conditional idea. You're talking to your friends, you're making a probabilistic decision based on their input, conditioning them, and then you're making an input. So, of course, the more flips you make, the faster you're going to solve a problem. Because for the factorization, for example, we need 200 billion flips. If you can take them in 2 seconds, that's going to solve the problem in 2 seconds rather than in 2 minutes, for example. So flips per second is the key metric. Now, just to calibrate you where we are today, computer architects actually report this number, thankfully. So we have something to measure. In these special graphs, highly parallelizable graphs, they're called checkerboard and chessboard. Let's not get into that, but just look at these numbers. They're amazing. 8 flips per nanosecond, 12 flips per nanosecond. Now, your computer in your clock in your computer runs around a gigahertz, right? I mean, you all know this number, gigahertz. Well, what is a gigahertz? That's 1 billion operations per second. But a flip involves many, many clock cycles, many, many operations. You're listening to your friend, you are doing an addition, you're having a random number, and then you're making a probabilistic decision. So that's a lot of clock cycles. But what they're saying is in these optimized GPUs, they can take 8 flips per nanosecond. That's 8 billion flips every second. That's a lot. And our work, the FPGA that I showed you, we can take it to 143, impressive, 143 billion flips every second. But you see, this is close to the GPU values because we are also using traditional present-day devices. But the idea is if you use something like an MTJ, let's say you have 1 million of them, everyone is flipping every nanosecond. You have 1 million flips per nanosecond. So that can take us to really computationally unexplored regimes. So we think that there's a lot of potential here. Okay, so that's the basic point. So FPGA is already competitive against GPU and TPU, but magnetic devices can take us to, to outer space, basically. And we measure this, we see, I'm looping back to one point I have begun. I said performance increases with number of qubits. Our architecture is really massively parallel. We put more qubits, there are more flips because everything is operating in parallel in our smart architecture, okay? So here I talk about our architecture a little bit. I'm not gonna go too much into details on this. I'd like your reaction and maybe we can discuss this a little bit, but let me just say that it's not easy to parallelize such things. You can't, because I'll give you the intuition. If all of us in this room start shouting, all at the same time, we're not going to make any progress in some intelligent discussion. It has to be conditional probability. I have to listen to Thomas. I have to listen to some others. We have to listen to them, right? So that's how we make consensus. So that's why we do some very nice tricks. We color the graph. We sort of make sure that everybody's listening to each other. We phase shift things, etc. But we're really trying to mimic this asynchronous, massively parallel architecture that I mentioned to you. And we're really trying to make it pseudo-asynchronous or truly asynchronous. We can talk about that if you're interested. There are certain things I didn't have time to go over. For example, sparsity is very important in hardware. In machine learning, people are kind of spoiled with all-to-all connections. They have a graph and they say that everybody can talk to everybody. In hardware, if you want to accelerate things, that's a no-go. So we invent techniques like we sparsify circuits. We said, okay, I'm going to come up with a new graph that's kind of a sparse graph. So I'm going to reduce the density of the graph. So all-to-all would be 100%, but we need to be like less than 1%. We need to have very few interconnects between p-bits. Overall, you can have more interconnects. It has to be sparse. And we try to kind of reduce the number of neighbors in a p-bit, p-circuit, etc. There's a lot of algorithm hardware co-design here. Sometimes we can do mistakes, but they still work. Here you are seeing that we increase the clock speed and time to solution goes down a little bit and then shoots up. So this is the shouting example I've given you. In the beginning where everybody is listening, everybody, but then we can be a little bit asynchronous. You know, Thomas can interrupt me, you can interrupt me, and we can still make progress. But if the interruption is too much, then if nobody is listening to everybody, and then time to solution in the y-axis goes to infinity, which means that you're not solving your problem. So there are these very interesting things one can consider, which is maybe I can break the hardware a little bit or break the algorithm a little bit to do very complicated things, okay? And some of you may be familiar with advanced algorithms. I mentioned simulated annealing mostly. There are things like parallel tempering, have replicas of the original sample, and don't let the system get stuck in one answer, which is the problem in simulated annealing and so on. I'm just showing you a flavor of the things that are kind of in the mix here that people are thinking about, finding new applications and new things, new algorithms, changing the algorithms and so on. This is not meant to be complete. It's just to give you a flavor of how this field is evolving. So this is my final slide. This is my summary. I've talked about implementing this new paradigm with p-bits. This is our architecture. It's really in between bits and qubits. I can talk more about that. You're trying to enter this regime of p-bit supremacy. That can you do something that you cannot do in classical computers with p-bits. And flips per second is the key there. If you can make intelligent probabilistic decisions, that's going to help out on a lot of problems. And what problems should we talk about? Well, look for naturally stochastic ones. And machine learning, AI, quantum computing are full of examples like that. So we believe that these p-bits could be useful in the domain of in the field of domain-specific computing as we go along. So with that, I'd like to conclude. I hope I'm not too much over time or this wasn't too intense. So please go ahead, and if you have any questions, I'd be happy to take them. Otherwise, thank you for listening.
No, thank you very much, Kerem. Thank you very much for this wonderful, very interesting talk. I enjoyed it very, very much.
Great, thank you.
Yeah, so are there comments, questions from the audience? There was one question from Louis Bennett, but as he commented that you already addressed it later on in the talk. So are there further comments, questions from the audience?
Right, so Louis Bennett's question is very interesting. He says he captures a critical detail in what I showed, and he's clearly paying attention that the 945 is a composite. It's not a semi-prime, right? 945 is. I hope that's what he's talking about. That 945 not being a semi-prime. In this case, our circuit doesn't know if it has to factor semi-primes. It just gives you the possible factors. So whatever, because it's like a multiplier. Whatever you give, whatever multiplies to my 945, it will show you. The reason we chose it, Louis, is because we wanted to go as large as we could. because at 945 was the largest, and it wasn't a semi-prime. So this was non-scientific reasons which you caught. But normally in cryptographically relevant problems, you obviously wouldn't want to factor an even number, for example. You would want to factor a semi-prime, right? Because what's the point otherwise, right? And for that RSA algorithm, this is key. But as I said, for us, this is just a hard optimization problem, not meant to be a real factoring algorithm yet. No implication along those lines. Thank you. Yeah.
Okay, thank you very much. Are there further comments, questions? Yeah, I have some questions. So, do I understand correctly that you program your computing device by these terms J, I, J? This is the key element to program it, right?
Yes, exactly. That is, yes. Yeah, go ahead. Sorry. Yeah, go ahead.
Yeah. Okay. And how can you change them? If I'm thinking on different problems, let's say this traveling salesman problem, how can I imagine that you program this problem with this p bits? Okay,
that again a very important key point that I actually didn't talk about at all. How do you program a given problem? First of all, what is this? I mean, Jij. I showed you one example where Jij was resistors. For example, here, if you look at this example, Thomas, it's like you are making a ferromagnetic. So you can write this in a 2x2 matrix, and you can say that J12 is G0 and J21 is also G0. So whatever you are doing with your system, the Jij needs to be programmable. These days we use CMOS technology to program, to store the weights and to program, right? So that's what's going on in the background. There's somebody that computes that. So first of all, there's somebody that stores the Jij and that computes the summation. So that's usually in digital circuits in my thinking right now. Now, if you have a problem like traveling salesman, okay, let's say that I can't program the Jij. How do I find the right Jij? How do I find the right Jij such that the solution will correspond to the actual correct answer? Now, there are two answers to this. One, you can write down heuristic optimization J's that you can say that, okay, think like if you said that, okay, I need to minimize this thing. Let me write down a energy function for which the energy minimum will be the corresponding solution to the TSP problem. This is a little bit of an art, and people wrote down, various Jij for these problems. Now, what I like to think about is a little bit different. I don't like this art business that, we should be more systematic. And there I have one method that is systematic, which I talked about a little bit, which is this idea that you can have something like this. Express your TSP problem as a Boolean circuit. And if you express it as a Boolean circuit, I can give it to a computer that will generate the Jij for it, because you have a universal set of gates. This is a little bit like quantum people talk about their generality, right? They say that, okay, I just need a universal set of quantum gates, a C0, a Hadamard, a Toffoli, whatever, right? A C phase or whatever. And then they kind of can generate anything. This is a little bit like that let's build these probabilistic copy gates, NOT gates, etc. And then, for example, you want a multiplier? Well, okay, just go find a multiplier circuit. Now, with TSP, I don't know if there's a good Boolean expression, traveling salesman. But if you tried hard enough, I think you could. But excellent question. Thank you for that.
Okay. Yeah. My second question is, some time ago, I heard a talk from a colleague of you about 300 kilometers in the south, I think, in San Diego, from Max D. Ventler about MRAM computing. And so remembering his talk and hearing now your talk, for me it seems that the concept is rather similar, or
Yes,
am I wrong?
No, you're not wrong. This is another important point, that MEM computing is being pursued by Viventra and colleagues. They have a company, and I think my impression is they strongly believe in this company, and their approach is rather similar. You're right. In a black box and architectural sense, it is similar. What I mean by that is, I think the way they factor integers is also through inverse multipliers. Okay, so and they also have terminal agnostic gate, an AND gate that can operate in reverse. Maybe I should have, before the factorization example, I could have shown you all how an AND gate works in reverse. For example, everyone knows 0, 0 will give you 0. But what if you fix the output of the AND gate to 0 and ask, what could have given rise to this output? Right? And okay, there are 3 possible answers, right? You can be 0, 0, 1, 0, or 0, 1. Now, this is a very fundamental thing, because in computer science, this answers the question of satisfiability. Can you satisfy, for example, if you fix the output of the AND gate to 1, can you find an answer that in this case of a single AND gate, it's easy. But for a circuit that is as large as the factorization, for example, we're really asking that question. Yeah. What satisfies this output? Now, these parts are very, very similar in MEM computing. However, what's inside is very different. As far as I'm concerned, MEM computing is not stochastic. It's an analog, continuous, so their state variables are different. I don't believe they have stochasticity. And there's another area that we differ with Viventra. I think for us, when we talk about factorization, we clearly see we clearly believe in or discover, we rediscover the NP, and we do not think, we do not think factorization, at least the way in which we are solving it, is anything but an exponential. I don't know if I've seen such a figure from them, or what their latest thinking is, but at various times I had the impression that they felt that this is actually changing the exponent from an exponential to some other, maybe polynomial. We have not seen such a drastic change, and we still think it could be very useful. You could still beat the GPU, TPU, go solve somebody's problem. I believe we also are common in that sense, that they are also trying to solve practical problems. But we do not think that we have any bearing, whatever we do has any bearing on the P versus NP problem. Things are very hard. Factoring exactly is very hard. And in fact, it's very clearly an exponential in our approach. So that's what I should say about MEM computing, I guess. Hopefully that's fair.
Yeah, thank you very much. I apologize for the nasty question, but
no, it's a very natural. It's a very natural question. They were very, very similar.
I think I remember. You're right. They don't have this randomness. You are probing randomly the phase space to find the ground state of the system. And I don't remember how they do it.
There could be emerging from in their approach, but probably not explicit, not in the update rules itself. Because you guys all know, there's ideas in chaos, for example, that without randomness can manifest even without explicit update. Randomness in the update rules. I mean, that's of course we all know that since chaos, but the approaches are similar. The philosophy is similar. The domain-specific approach. So there are many other examples in photonics. There's this coherent Ising machine. There's Fujitsu, Hitachi. So it started as kind of a new lonely thing, but now I feel like it's becoming a sort of a subfield or even a field as we go along.
Okay, yeah. Thank you very much, Kerem. Are there other comments, questions from the audience? Yeah. If this is not the case, then Kerem, thank you very much again. I enjoyed it very much.
Thank you for
very clear, very nice talk and beautiful work. My congratulations. And
thank you very much. Thank you very much.
I hope to see you the next time in person here in Mexico or in California.
Absolutely. Let's keep in touch and greatly appreciate it. Okay.
Thank you. Bye-bye.
Bye.